Hey everyone, welcome to the video on chapter 11.3. In this video, we are going to discuss about physical properties of amines. So first of all, let's look at the physical properties boiling point. So recall back that boiling point, it relates to the type of intermolecular forces and strength of intermolecular forces between the molecules. So for amines, both primary and secondary amines, they can form intermolecular hydrogen bonds between its molecule. So more hydrogen bond can be formed in these primary amines. So let's look at the structures of these primary and secondary amines. So this is a molecule of primary amines with its molecule. So this is the internal hydrogen bonds. And then similarly for this secondary amine, here is your hydrogen bonds between the molecules. So for tertiary amines, they do not have the hydrogens atom, therefore they cannot form any intermolecular hydrogen bonds with each other. So for this tertiary amines, it's only have the weak van der Waals forces. Okay, can take notes over here. Yeah, tertiary amines has only weak van der Waals forces. If you want to compare about the boiling point. So amine has higher boiling point than alkanes and haloalkanes of comparable molecular weights due to the formations of this intermolecular hydrogen bonding between the molecules. But they will have a lower boiling point compared to alcohol and carboxylic acid. Okay, this is because hydrogen bond in amines is usually weaker compared to the one in alcohol and carboxylic acid. The main reason is nitrogen is less electronegative than the oxygen. Okay, and therefore it will result in a weaker hydrogen bonds in this amine. Okay, NH bond is less polar, result in the weaker hydrogen bonds. So this one refers to the amines. So examples given over here, you can see an alkane, haloalkane, amines, alcohol, carboxylic acid. So the molecular mass is almost the same. So we call this one comparable size. Okay, and then you can see over here increasing in boiling point. Okay, due to the differences in the intermolecular forces. So this one London forces, this one you got the dipole-dipole. You got the hydrogen bonds, but with less electronegative nitrogens, alcohol hydrogen bonds as well, with more electronegative oxygen. And then carboxylic acid is stronger because it exists as dimer through hydrogen bonding. Okay, can practice about the explanation. All right. So the second physical property is solubility. So solubility, it depends on what is the solvent that we use. Okay, and then it depends on the ability to form the bonding with the solvent given. So in this one, we are talking about solubility in water. So all amines having 5 carbons and below are water soluble because they are able to form these hydrogen bonds with water molecules. And for those amines which have more than 5 carbons, that means 6 carbons and above, they are mostly water insoluble. Okay, as the molecular size increases, the hydrophobic area or the alkyl portion increase, therefore solubility in water will decrease. So this is the examples of the diagram. So here you got your primary amines, okay, secondary amine with 2 alkyl groups. They make the hydrogen bonds with the water solvent molecule. Okay, and then take note that for this tertiary amine, it can also form the hydrogen bonds with the water molecule, as this nitrogen has extra lone pair. Alright, so next let's look at this solubility in organic solvent. So most of these amines soluble in organic solvents, for example, alkane, alcohol, ether, regardless of the size. This is due to the ability to form these van der Waals forces or London forces between the amines and the organic solvent molecules. Okay, so be aware that what is the solvent given in the questions? Is it the organic solvent or is it the water molecules? The next important physical property for this chapter 11, we are talking about basicity of amines. So amine is a nucleophile, or we call it a Lewis base because it's lone pair on the nitrogen atom. So this ammonia or any of this ammonium derivative. So this lone pair is going to be donated Okay, and then you're taking another hydrogens to form this ammonium species. Okay, ammonium species, and then generating the OH minus. So from here, we know that this ammonia or ammonium derivative, they are basic. And then the strength of the base depends on the ability to donate the lone pair electrons or nitrogens, and the stability of the conjugate acid, alkyl ammonium ion form. Okay, so for this one in the diagram here, because you're using ammonia, so you're forming ammonium ion. All right, so let's look at this diagram. It concludes the factors affect the basicity, and then the same thing, it categorized into resonance effect and inductive effects. So talk about resonance effect.
Presence of resonance structures stabilize the conjugate acid,
and it reduces the electron density on nitrogen, make it less able to donate the electron, and therefore it reduces basicity, or the amines become less basic. Whereas for this inductive effect, we have electron donating group and electron withdrawing groups. So examples of electron donating group, alkyl group, it will increase the electron density on nitrogens, which stabilize the conjugate acid. So in general, we said that in the presence of electron donating group, it will increase the basicity of an amine. Okay, or the amine become more basic in the presence of EDG. On another side, in the presence of this EWG, so EWG will decrease the electron density on nitrogens, making it less able to donate the lone pair. So it destabilizes the conjugate acid and it decreases the basicity. So amines become less basic. So first of all, let's look at this inductive effect. Okay, an alkyl group is an electron donating group and it will increase the electron density on nitrogen's atom. When the number of alkyl group increase, the electron density of nitrogen's atom increase. Lone pair electron can be easily donated. Basicity increases. So if you look at the diagrams over here, ammonia with no alkyl group forming ammonium. Methylamine has one alkyl group. This is your primary amine. And then this presence of EDG, electron donating group, will donate the electrons towards these nitrogens, making it more able to donate out its lone pair. Okay, therefore it stabilizes the alkyl ammonium ion form. Okay, this ion is stabilized by the presence of EDG. So alkyl groups are electron donating groups. They stabilize the positive charge on the alkyl ammonia ion through inductive effect. Therefore, for primary and secondary amines are more basic than ammonia. Okay, remember ammonia doesn't have any alkyl group. For primary and secondary amine, the basicity of amine in gaseous phase and aqueous phase increases with the increasing of alkyl group. Or in other words, we say the secondary amine is more basic compared to the primary amines. At secondary amine has more alkyl group. But for these tertiary amines, its basicity is different in both phases. That means in gas phase, the basicity is different. For aqueous phase, the basicity is different. All right, this is due to the steric effect. Okay, steric effect apply to this tertiary amines, yeah? So steric effect refers to the crowding of alkyl groups around the nitrogen's atom, which hindered the lone pair to attack a hydrogen's ion. Thus, the basicity decreases. So this is in the meaning that if this amines exist in the gas phase, basicity of amines depends only on the numbers of electron donating groups present. So tertiary amine with more number of alkyl group has the highest basicity, followed by secondary amine, primary amine, and then ammonia with no EDG or electron donating group. But be very careful that if you have this amines in aqueous solution, aqueous phase, so the order of basicity in aqueous solutions depends on both the number of electron donating groups and the steric effect. So now the sequence, secondary amine will have the highest basicity, followed by primary, then only it will reach this tertiary amine. Okay, so aqueous phase, even though you have this higher number of alkyl group, but due to the steric effect, it blocked the way for this lone pair to be donated. Okay, so beware about the sequence. Secondary amine, primary amine, tertiary amine, then the least basic will be ammonia. So this one is in gas phase. The bottom one here is in aqueous phase. And lastly, let's look at this resonance effect. So aromatic amines, which is the aniline, are weaker bases than the corresponding aliphatic and cyclic amines. Alright, so comparing between two of these kind of similar structures, but one of it is aromatic amines with nitrogen attached to a benzene, and then for this one is an aliphatic amine. Okay, the name is cyclohexylamine, the common name. So looking at these aromatic amines, delocalizations of lone pair electrons into the benzene ring. So imagine that this lone pair will then delocalize into the ring. Okay, so delocalizations happen, which stabilize by this resonance effect. So the electron density on the nitrogen decreases, making it less able to donate the lone pair electron. Therefore, aniline, the aromatic amine, is less basic. Whereas if you have this cyclohexylamine, so this is a cyclic structure, which also known as your cycloalkyl group. Okay, an electron donating group. Okay, this one, electron donating group. So this cycloalkyl group will donate the electron density towards your nitrogen, making the lone pair more able to donate it. Okay, so lone pair on electrons are localized. Electron density on nitrogen increases, more able to donate the lone pair electrons. Therefore, cyclohexylamine is more basic. Alright, so aromatic amines or the amines need to practice drawing the resonance structures in which a resonance effect show the delocalizations of this lone pair into the benzene ring. Okay, so lone pair forming the double bond, and then with this negative charge at positions number 2, number 4, number 6, and then back into this nitrogens again. Okay, so resonance effects of aniline. Delocalizations of electrons stabilize the aniline, okay, or stabilize the aromatic amines. So it decreased the electron density on nitrogens, making aniline less basic than the other types of amines. So in conclusions, with the presence of resonance effect, the basicity decreases. And so try one example questions below here. Arrange the following amines in ascending order of basicity. So you are given aniline, cyclohexanamine, p-nitroaniline. So the structures of aniline look like this: NH2 and attached to the benzene ring. Cyclohexanamine, a cyclic structure attached to this NH2. Another name for this cyclohexanamine, we also call it as cyclohexylamine. And then you have this p-nitroaniline. So at positions number 4, you have a nitro group. Okay, NH2 for this aniline, and then NH2 is the nitro substituents. So again, the same thing, we label it as KLM, and then we interpret one by one. So for this NH2, this aniline, we have the resonance effect presence. So resonance effect reduce the electron density and then reduce the basicity. Okay, we take notes a little bit. This one will reduce the basicity or become less basic. And then for the structures of L-cyclohexanamine, this one is your electron donating group. Okay, an alkyl group electron donating group. So presence of EDG will increase the basicity. Okay, making this amine more basic. And then finally, for this p-nitroaniline, you can see the benzene ring. That means the lone pair of the nitrogens can delocalize into the ring. So that means there's resonance effect present for this p-nitroaniline. And at the same time, it has the presence of EWG. Okay, both effect are resonance and EWG. So it will further decrease its basicity. Okay, further decrease its basicity, making it much less basic. So according to this ascending order of basicity, you start with the least basic, which is this p-nitroaniline. Okay, M. Followed by the aniline, which has this resonance effect. And then the most basic come from this cyclohexanamine, as it has the electron donating group, which make the lone pair easier to be donated. So please have a try at the exercise 11.3, and we will discuss during the tutorial sessions.